So once again, Isaiah Jaramillo, work for the Natural Resources Conservation Service of USDA, and I am a resource soil scientist along with Cole, or John Patton. So the presentation we're going to go over today is just a little bit about the soils and land use section of Envirothon, and the presentation was kind of based around the learning objectives that were online.
Again, I'm Cole Patton. It was John. John's my first name. Like, keep people confused, I guess. So, what is soil in relation to kind of our topic? It's the combination of air, water, organic, and mineral matter. Soil is a living body. When you dig soil up and put it on the concrete pad over there, then it becomes dirt. There's soil and dirt, right? There's 5
soil forming factors.
Forming factors. Thank you. There's climate, which is the climate that you're in and how it's developed over time. Organisms, so all the microorganisms, all the biology that's in the soil. Parent material, so that's basically the geology, like what are the rocks? Is this soil weathered from sandstone? Is it glacier till? Is it loess? And then relief, and that's basically like topography. And time, of course, the time it takes to weather down sandstone or parent material.
Yeah, and we'll go over each of those 5 soil forming factors more in depth in the next couple of slides. So the 4 components of soil, they comprise of mineral, organic, air, and water. The mineral material can be anywhere from little clay particles to boulder-sized mineral material, organic material. We look at the landscape, grass, trees, or any soil biology under the ground. And then pore space, and that can consist of, once again, the liquids or water and gas. And each one, so the mineral and organic material and the air and water, each comprise of 50% of the pore space. And the 50% pore space can fluctuate based on the types of soils.
So I jumped the gun there. So the 5 soil forming factors, that's what I was trying to remember, was CLORP. That's the acronym. I guess we're the government. We're great with acronyms. So climate, organisms, relief, parent material, and time. Go into climate.
Yeah, so the first one, like Cole mentioned, when we talk about climate, temperature and precipitation, those are the main factors. And when you think about water, water makes a lot of reactions go, right? We think of chemistry, we think of natural ecological cycles. So those 2 are the most important. And when you think about that and relate to soil, so if you go more on the southern hemisphere and you look at the equator, that's where we have the most developed soils in the world, or oxosoils. They're highly weathered. You'll see a lot of color in those and a lot of different characteristics that point to there's a whole lot of reactions going on in the soil.
Which brings us to organisms. Just briefly, this is a whole maybe year study or college course in microbiology or biology in the soil. And really what it boils down to in a health or forestry health perspective is, are we keeping the soil covered in temperatures? As we keep soil covered, it keeps soil temperature cooler, especially, we're in Texas here, so we know it's pretty warm here, it gets hot. So as temperature rises, I think it's 100, don't quote me, I have to look it up, but I think it's 140 organisms in the soil start to basically disappear or fry, and then 165, they're completely gone. So as we cover the soil, we are able to keep moisture, keep the radiant heat off the soil, keep that microbiology flowing. And so all those rhizopheres, there's all these organisms that are living on the plants. They're dying in there, they're cycling nutrients, and all that's kind of the process of the organism part of the soil formation.
Mm-hmm. And something to touch on that, the soil ecosystem, it's without a doubt the most abundant, most biologically diverse ecosystem throughout the world. And just in a handful of soil, you'll have billions of different types of organisms. So something to note. So with relief or topography, basically it's just the slope of the land, the general configuration. So if you're going to take anything from this slide, just know that when you have low-lying areas, you're probably going to have more developed soils and deeper soils, while on shoulders or back slopes, you're going to have thinner soils, as these areas are less water receiving. And kind of getting back to that, so water makes a lot of reactions go, right? Makes deeper soils, while on those ends, those shoals and back slopes, the water is shedding, and also the material on those slopes is shedding and getting into those lower lying areas, leading to more developed soils.
Yeah, so I want to add a couple things on this. This is a cross section or hill slope profile. This is essentially a soil scientist or soil mapper's Bible, or what they live by to map soils. So, like if we're sitting right here and we're looking out, out this window here, we see that what on this hill slope where do you think we are on this hill slope profile? So we have the summit, shoulder, base slope, foot slope, and toe slope. So is there a river over there? I'm not sure. Probably that tree line out there. So we got a river there. So this is the river. So we're probably in the foot slope. Agree? So somewhere out in there. So the most eroded part of this hill slope is going to be the shoulder. So that's like you said, that's the thinnest soil. And what's actually happening is a colluvium process where this soil is eroding down this hill. So everything, up this, wherever the highest point here is, everything has gone and it's shifting down. And this is to where we get to the alluvium. So essentially, you're losing up top and then gaining at bottom. So soil goes, roads kind of downhill. Which brings us to the parent material again. This is the alluvium quaternarium. This is the area that we're in. Soils are derived from the sandy, loamy, and clay sediments. So that's kind of back a couple slides where I was talking about, sandstone. So we could get out in this part of western Texas, a lot of sandstone, a lot of wind erosion. So a lot of those soils are like aeolian, what they call it, deposits. So it's sandstone that's eroded. We get down here, and this is what's really interesting about Texas geology, and quite honestly, mapping some of these soils in my career is some of the hardest soils to map. Out here, you could go out there and you can see 40, 30,000 acres, and we used to call it windshield mapping. You can go out there and sit on top of a hill and just start drawing lines out on your soils maps. And that's mainly because there's broader geology. You get over here and you see all these little narrow bands. So those are all different geologies. So meaning they're all different soils, and it's all different time periods. So what basically has happened is, here's your beach. This was a beach. This was a beach. This was a beach. So all those, older geology versus younger geology. So this here is your youngest and goes this way up to oldest, which is why they find shark teeth and all that in Panhandle and all that.
Mm-hmm. That gets to the law of superposition. So like Cole said, the oldest stuff is on the bottom and then the younger stuff gets on top. So this is a kind of law that ties into geology, archaeology, and other fields, or you can call these different layers stratigraphy. And as it relates to parent material in Texas, this slide kind of shows you that in how the geology relates to the different geological timescales in Texas. So Cole mentioned, parent material, to kind of understand the concept, can get a little confusing. With parent material, we also look at it in how it was deposited, right? Cole had mentioned eluent. You also have residual, colluvium, and alluvial. And I'm not going to go into each one. We're going to provide the slides so you can kind of look at each one. But different types of parent material are deposited in different ways, and it's based on this diagram. Is it deposited by wind, water? Is it just coming off a slope through gravity and different things like that?
Yeah, so colluvium, I mentioned that word earlier on the hill slope. So just remember, soil from on top of the hill moving downward to the bottom, that's colluvium. Alluvium, so that's water. It's water deposit. Some key indicators. Now I'm getting a little too bored, but indicators would be like rounded gravels, things like if you think of Colorado stream, like all these rounded, Colorado River rock, all that. That's all been washed over. It's rounded. Water's been taking all the edges off of those rocks. Again, time. So soils on floodplains and along the coast are younger, like we discussed in that geology map. It takes about 500 years to form an inch of soil from hard parent material.
Which is one of the main reasons why we got conserved soil, right? I mean, it's a natural resource, right? It can take anywhere from 100 to 500 years to make just an inch of soil from that parent material, which is really important. I mean, we don't want a whole bunch of soil going into the Brazos River, as once it's gone, it's gone. So we gotta have as much conservation on the ground as possible, and that includes having good covered soil like this.
One thing, again, back to protecting that is, not overgrazing pastures. I could see, like, we're sitting here 500 years where, let's say we had 30 inches of topsoil, which is kind of rare in Texas, honestly. And, we get out there and we throw 400 head of cattle on 100 acres, and then it gets grazed down on the bottom. There's no grass. We get a substantial rain, and you lose 15 inches of that to the Brazos.
Mm-hmm.
Well, you just lost, 500 years of topsoil in a matter of one rainfall event. And so that's kind of the thought process of protecting your soil.
Moving on from the soil forming factors, once all these soil forming factors does its work on the soil, you'll start to see the development of soil horizons, and this snapshot is called a soil profile. Just in simple terms, your A horizon is going to be the most biologically active and the most nutritious, while the B horizon is going to have a little more clay content, and it's going to have accumulation of different minerals like iron, aluminum, gypsum, sodium, different things like that. While you have the C horizon, that's where you'll actually see the parent material, or the material that the soil is actually forming from. And here you'll also see a lack of soil structure, which we'll get into soil structure in the next few slides.
So what is the state soil of Texas? Anybody know the state soil? Anybody know the state bird? All right. Well, there's a state soil. So Houston Black is the state soil of Texas. Houston Black.
Yes. I included this slide just to show that simple soil profile isn't usually what you see. When they're describing soils and get all information together, it'll look something like this, where you'll have your master horizons, your A, B, and C horizons, and then next to those capital layers, you'll have different lowercase layers or suffixes that detail more specific characteristics within that soil profile.
Yeah, so what's interesting about that is the horizons, like we talked about the A, B, and C. So a lot of times those are easily differentiated between soil color. So you could have a dark A horizon and then a lighter color E horizon or B subsurface. So very often soil color is a huge indicator, but I don't want to jump ahead here. So
we'll get the soil color. Soil texture, without doubt, the most important physical property. This is going to determine how much water or moisture as well as air can be contained into that soil. And we'll do a soil texture demonstration outside to kind of show you a few of the 12 textural classes that are designated according to USDA and RCS.
So soil particle sizes. So the largest particle size class is sand. The next size would be silt, and the actual smallest particle size is clay. That little diagram there is kind of a representation of that. Sand, beach, just think of beach sand, like you're on the beach. That's, real coarse, loamy sand. Silt feels kind of like powder, and then the clay can be like modeling, like think of like, not necessarily Play-Doh, but like modeling clay, like pottery clay, things like that.
And here's just a diagram, and I believe y'all printed these the past couple of years, but it's a really good diagram of showing you a qualitative approach to see what type of soil you have. When we do soil texturing, it is backed by quantitative data, so laboratory methods, but this is just a really good way to essentially see what are those texture classes you have, and this is going to be really based on the ribbon length, going to be based on the amount of clay in the soil.
We'll get into kind of sandy clay and I went through loam.
Yeah.
Okay, so clay. Some pros of having a clay soil: typically the pH is pretty high, 8, 8.4, something like that. Usually have high organic content. I drove through Sealy over here. And it's all, it's probably Houston Black, honestly. I don't remember what it was mapped, but, that's your cotton, corn. So those are typically your high productive soils. Problem with that, since this is the soils and land use workshop here, is what's happening on a lot of this farmland that's right on the edge of town.
It's being built on.
Yeah, we're building all these subdivisions on this high shrink swell clay. Maybe right now, 5 years, building all these houses with these slabs and all that on these high shrink swell is fine, but maybe 25, 30 years, we start having foundation problems. I'm originally from Central Texas, around Temple, and I know my parents built on a high shrink swell clay, and they've had foundation problems my whole life. So it's, they're always having foundation guy, Troy and people, whatever, coming in there and jacking the house up. But
yeah, and Temple's right smack dab in the Blackland Prairie, which is, you can see all those clay types of soil.
And those are things to think about. There's some things that can be done to backfill and do all that on, limitations and suitabilities for high shrink soil clays and all that. We'll move on to sandy.
So sandy soil, just kind of a disclaimer, none of these, whether it be clay, sandy, or loam, none of these are bad soils. They're just going to be good for different things, right? And one of the pros of sandy soil is you have rapid infiltration, which is better drainage. So you're not going to have a whole lot of ponding issues or compaction issues. Now the cons is, in contrast to clay soils, you're not going to have as much organic matter buildup. You're not going to have as much fertility, and it can't hold water as well as clay, right? But getting back to not necessarily not being as good as clay soil, sandy soil is actually good for growing things like peanuts or timber production.
I would say one of the major limiting factors on a climate aspect would be rainfall. If you have a sandy soil, you definitely need a lot of rainfall. Loamy soil, that's right there between clay and sand. Is it the perfect soil? Is there a perfect soil? I don't know. I've seen a lot of these garden things and, Master Gardener, all this different stuff where, you want to shoot for the loam. Well, yes, maybe, but it just depends on what you're trying to accomplish. Again, back to the loamy, it always has the favorite from all the gardeners, I guess, but it's low to high fertility. It's moderate to work with. So yeah, it is kind of the medium between, all of it.
I don't know if you want to touch on this, Cole, but you were talking about a little bit about different types of soil in forested areas. Soils in the pine woods and coastal flatwoods out there in deep East Texas, you're usually going to have more acidic soils, or pH below 7, and the surface texture is going to be sandy to loamy, while the subsurface, or you call it the B horizon, is going to have loamy to clay subsoils, while in that area has a lot of timber production.
Basically, if you thought of, in this mind frame of sandy, more acidic, and clay, more alkaline, and that's pretty much where it lies. Thankfully, like East Texas, piney woods, you get 60 inches plus or minus rainfall year, so the acidity is not as bad to deal with, but that's where your blueberries, pine trees, things of that nature excel or do well in. Lower rainfalls, you could probably do better with less rain. Just making an assumption there, but because you have higher water holding capacity. Again, like in these flat woods, piney woods, they're sandy and they get a lot of rainfall. What am I say about that?
Yeah. So soil color, we're going to do a demonstration outside. The way it's broken down is by hue, value, and chroma. And just from a basic standpoint, when you look at soil color, the darker, the more organic matter, which can relate to soil fertility. The lighter, you're probably going to have less fertility due to less organic matter. But in reality, the color derives from the parent material.
If you haven't seen one of these, I'd recommend you get one and help your team. You could look at it as like it's the paint chip thing at Lowe's or whatever, but it's just a way to scientifically categorize a color.
Yeah. And there's really no perfect way. Everyone is going to see colors differently, right? Whether it be something in the 10-wire hue. It's just all subjective.
So models, redoxymorphic features, what is all that? Well, around this area, you probably see a lot of this. If you took a nail, a brand new nail, and you stuck it in that water and left it in there, as long as it stayed in the water, it's going to stay gray, or let's just say it was a gray nail. And then, but as soon as you pull it out and expose it to air, what's happened is it's become oxidized, and the iron in there, and it rusts. The same thing happens in the soil. So there's again, don't quote me, but there is a high percentage of iron in the soil. And so that is what happens when you see these red and yellow, orange colors. That's where water has been. There's a few things that could happen there. Water table could come up and it's saturated, or we get a rainfall and water is moving downward through the soil. So there's water in the soil that is then become oxidized that creates the red, orange, yellow colors. So if we go to a soil, dig a hole, and it's solid gray, what's happened there is it's in a reduced state. So the gray color is your indication that the soil is wet.
Yeah, and here's just another color kind of touch on that. So well-drained soil is going to have water moving through it pretty easily, while poorly drained is going to keep that water in the area, making it that reduced iron color, or that's also a key indicator of hydric soils, that color.
So if you, I don't know
It's
if
a little hard to see.
I don't know if you can see this or not, but there's some right here, just a reddish brown. That's probably like a 10-wire 4-6 color. That is probably where a root was. So it's an oxidized root. Like there's little streaks through here. So that's where some pore linings, and this is what we would call oxidized root channels. There's some gray in here. So we would call this, if we were describing that soil, it'd be like a 10-wire 5-2. So it'd be a gray color, and that is where you're saying this soil is wet. You're saying that there's oxidized root channels, and essentially what you would say is you have a hydric soil, which at the very beginning could be an indicator of a wetland.
And here's just another picture showing that iron depleted soil. It's kind of hard to see here, but there's just a big gray mass right there.
Soil structure. If you don't have one of these field book for describing soils, I don't know, we'll have to share the link. I don't think
it'd be
put
kind of hard
that,
to get
but
some.
this is something that you could order. I think you can go online, but these are very handy to have because it has all these, everything that I do or we do in our jobs and describing soils is in this book, and we use this very heavily. It describes what we talked about so far is everything in here. And so it's a very handy book. It's called the Field Book for Describing and Sampling Soils. The soil structure, these are different structure types. You have granular, which that's going to be probably your most, that's what I call like your granola or your, that's like your goal. Like you want granola soil. Like when you're going out there in the garden in your raised bed or whatever, and you're picking it up and you see it all kind of crumbly like granola, that's it right there. The platy, that's pretty much compacted soil. The prismatic, the wedge, these are going to be, this wedge shape you're going to find in high smectitic clays. Massive, that's typically going to be like where you're going to describe like your sea horizons. Blocky, this is real common, probably the most common soil structure. And then single grain, that's going to be all your sand.
And here's just a couple pictures of each of those. Now, you'll see some of these structures more in certain types of soil. For example, you'll likely see platy or blocky structure more in clay soils, while like Cole mentioned, single grain, it can be just sands, or think about it like on a playground where the dirt is just getting your hand, it's just going to fall between your fingers. That's structureless or single grain. While the picture's not here, but the massive, think about it like these huge clods of soil that are left over when they till the soil, or just think about big clods. I mean, it's in the word, right? Massive.
Yeah, so that crumbly, granular. This is kind of what that granular structure that I was talking about. We could get into weeds there and talk about. Somebody might call this weak, fine, angular, blocky. So like all the edges on all these are what we call PEDs. There's flat, steep edges there. For today, we'll call that granular.
Yeah, and the
Good,
top,
healthy.
you could call it, if you disturb it a little bit, you could either call it massive or single grained, that structureless soil. So soil pH, the ideal range to have for a soil is 6 to 7.5 pH, as that really allows you to have the most amount of plant available nutrients, like you can kind of see on this chart here. And here are a couple different methods you can use if you have a soil that's either too high or too alkaline or too acidic. So there's 16 essential nutrients, and they're broken down by primary, secondary, or trace elements. And in the next slide, it'll kind of show you a diagram of those nutrients as well as their functions within the plant. So one thing to know is that a plant needs all these nutrients because the plant growth and health is going to be limited by the nutrient and least supply. Yeah, and here's the chart I mentioned with the different types of nutrients as well as their functions in plants. It's a pretty good read, and we also include some sources of where to find them. And a lot of these PDFs or documents are from Texas A&M AgriLife.
Soil sampling is very important in knowing, number one, is a fertilizer recommendation needed? Do we have a lack of an element? And then also how we're sampling that. So there's, not to get too far into this, but just looking out here, we see this huge pasture over here to the left. It's probably not all the same soil. Like there's probably a soil map and it has some minor components. So an effective soil sampling scheme would be maybe collect several different samples all throughout the area and not in just one area, so you get a more accurate sample.
Yeah, and when we're talking about soil samples, we're getting a lot more urban producers. So actually, Texas A&M has an urban soil survey form that you can fill out. And one of the things they're actually doing now is heavy metal testing, because obviously as we're growing in these areas that used to be either factories or they've done some type of production that heavy metals like lead is being deposited on, they can actually test for that. And us at NRCS, the research soil scientists, have PXRFs, or portable X-ray fluorescence, that will detect a number of different heavy metals in the soil using radioisotope.
There's several different ways of doing the nutrient analysis. They're listed there. Like you were saying, we have the handheld PXRF where we can go out and take a sample within 3 seconds, 5 seconds, something like that, and give us a quick elemental analysis.
So soil surveys. So I guess back then, the soil survey offices or soil survey division of NRCS would put out these publications of soil surveys, right? And they function just the same as Web Soil Survey. I don't know how many of you use Web Soil Survey. And just a quick plug right here. So if you guys have a smartphone, I would recommend you guys download Soil Web. I don't know how many of you guys have Soil Web on your phones. That's basically a app version of Web Soil Survey. And it's really good. You can go anywhere and see what mapping is there, as well as different qualities and limitations of that soil in your area. So it's a very, very useful tool there. But getting back to the soil survey,
if you go to your app, type in Soil Web, it's a free app, and it'll give you access to all the soils information in United States and territories.
Mm-hmm. Yeah, these soil surveys, just kind of a little disclaimer, they are out of date in terms of the maps and mapping, but there's still a lot of good information in these publications that you can read on that you might not even be able to find online or on Web Soil Survey. So I know a lot of the older soil scientists would collect them like trading cards, right? Get one of all the counties in Texas, and I'm actually trying to do that, so it's kind of a cool thing.
Major parts of the soil survey, again, this is like the historical, like if you went online and typed in historical soil survey of Matagorda County, you'd probably end up finding a link to this. And this is basically, so there's Web Soil Survey, that's what's the internet platform now, but this was the paper version of that before we went internet,
Mm-hmm.
I should say. And again, so this would be everything that's in there in a paper version.
Yeah, so using the soil survey. So at the back of the publication, you'll find these maps or these little grid maps. And what you'll do is locate the area you're in or relative to the area you're in. And then you'll go, I believe, back a few pages and you can see what map units are in your area. And we could get into, what map units are. But basically, in a nutshell, what map units are a cluster of different types of soils. Or like how we mentioned Houston Black, that's a soil series or one type of soil.
Yes. Again, like if you were to download or look at Web Soil Survey, or if you download the Soil Web, you'd go to get my location, bam, and then it puts you on a spot on a soil, and you'd click that soil, and you'd say, let's just say it's Houston Black. So Houston Black would be the major component. And then within that major component of soil, there are what are called minor components. So if I started right here and I went to that house down there and I dug 10 holes from here to that house, I would say, or let's just put as an example, 7 of those holes, I would describe them taxonomically as Houston Black. 3 of those would be a minor component, and we'll call those Bernaldo clay. That is how a map unit is made up. Not all, very, very, probably not even accurately, and this is probably why we still have a job, is that there are some map units that are mapped 100%. This is my opinion. I don't think that's accurate. I don't think you can have 100% of a map unit potentially, because you're going and saying that every hole, from here to that house, for example, is going to be the same. There's just too much, variability. So, and that's what this slide is talking about: inclusions, and then the map unit name. So Houston Black is the map unit name, and then it goes into the descriptions and all that. So the tables, again, this is all prior to internet. This is paperback version. So everything that you're getting in the app or whatever, this was in a paper version. So the summary tables, the woodland management and productivity, wildlife habitat. So all those summary of tables, those are basically all your interpretation. So let's take Houston Black again. Say I went into the Soil Web, georeferenced my area, and I was looking at it, and it says suitability for foundations, and it was red. So I would look at that, and it'd say not suitable, or
Like unsuitable?
yeah, something you have to overcome to make it good. That is what all these tables, and that's how these soil surveys were made. It's just in the paper version of that. Again, this is, kind of tie this back to the hill slope. This is like the soil scientist's brain right here. Like when, I was out there mapping like West Texas. I'm sitting on top of this Eckert, so I established that as the soil on there. I was on top of the hill, and then I was looking down at all the valleys, all that. I could see it all out because I'm in West Texas. There's no trees, right? So I'm out there and I'm seeing all these, slopes, cuestas, and all this. And so then I'm able to, I would traverse, sample all these and get an idea. But then you can start overlaying those on block diagrams. So this is a block diagram, and this is how I would relay to you, 50 or 100 years from now, what I was doing then. I wasn't just out there, eating lunch under a windmill or wind turbine. So there are different type of map units, and this kind of describes those. There's inclusions. There's what I was been talking about, like the 10 holes. 3 of them are different. This is how they're all incorporated into the map unit, and this is what these slides are talking about. And there's different kinds, associations. That's just the different names of the map units. Mm-hmm. Complexes, when there's 2 different soils and you can't differentiate between the 2, so you stick them together. So that'd be like a paint horse. Is it red and white, or is it white and red, or zebra? Mm-hmm. So let's just stick them together and call it a zebra. Complex. Any questions?
You know if they're going to be using those surveys?
Yeah, for the content, I'm not too sure.
There's 2 ways we color to classify soils. We typically take the wet color. So when you do let's just say we took this out of the ground. Can you hand me one of the water bottles, please? what we typically do is take a bottle or whatever, and we just wet it. So we want a wet color or moist. It's actually called a moist color. And then 10YR is typically the predominant color to start with. What I always tell everyone.
Which one?
10YR.
10YR.
Yeah. So this is the hue. Is this the value? Is these numbers, and then the chroma is this way. And so I would go in here and always take a little ped. These are called peds. And look, you just match the color up. Oh, sorry. Man, I just messed up big time. You always color in the sun.
Yeah.
So to me, it looks like a 10YR 4-3. So as you go that way, you're browner. As you go this way, you're redder.
Yeah.
So if I did 7.5YR, maybe it didn't look as good that way. That actually probably looks a little better. So 7.5YR 4-3. So what is that? So that's that's the hue value chroma, which will also tell you. So 7.5YR 4-3. So brown. So, and then basically these are indicators. Like if we were like a 5.1, it's gray. So do y'all remember what gray was an indicator? Wetness. Yeah. So we would have a notion or an idea that this soil may be influenced by water, or might be a hydric soil or some nature. Unfortunately, there's no redox, and that would have been that yellowish brown, all those. But those colors are going to be like what we saw in that slide, the yellowish brown streaks. Those are typically going to be over here in like this 4-6, 4-4 colors. Those are always like your redox colors.
Now, if it's streaked, which color would you use? Would you blend it,
So
or would you use the strongest color in it?
So the predominant color is your matrix. So you have to determine this right here is our matrix. If there were streaks in this, those would be the redox, or they could be nodules. Don't want to get too far in that, but there could be other smaller percentages like 3%, 4%, and you're saying like this is 80 something percent matrix color, and then all the others make up 4-6, 5-8, all that, and that's all all these over here.
So you just do the dominant, or do
Dominant
you find
color.
the others and put the percentage on it too, for like you just do like dominant,
Yeah,
and there's like streaks.
Yeah, I would try not to make this too complicated, but I would stay with the matrix color.
Okay.
And like so there's and you can really go like there's a black, there's an iron manganese concretion in there. It's black.
Oh yeah.
So you would essentially we would color that too, but I'm not. We're not gonna get that far.
When they describe soils, like how he mentioned doing like transects, then they would note all these little things.
I'm trying to think what else on that.
As you can see, very subjective. I mean, me and Cole are probably going to see colors a little differently, but there are some safeguards, like, whether I get 10YR 5.2 or he gets 10YR 4.2, we're still going to both fall into the brown category.
Mm-hmm. And one thing I said at the very beginning, which will be indicated on, I guess, the test or whatever question, if you are coloring, it will note whether it will be dry or moist. Yeah. So if a dry color, you would air dried out, as you pull it out would be the color. If it wanted a moist color, you would moisten it and then take the color. A lot of times they will be at least one chip different.
Aren't they always supposed to be moist for those books, or no?
No, we do a air dry. I will say on the color chip difference that I've been involved in wetland determinations in the last few years. It can come down to one chip being how do I put this? Making wetland, I
Protected
guess.
versus not.
So it can get pretty.
Yeah.
I didn't really comprehend that really till I started really doing it, and like you could have a, let's say on a cloudy day, I call this a 3-3, and so I would say this soil is not hydric. This won't be a wetland. Well, I come out on a sunny day, and it was 3-2. Well, now that meets the criteria of a hydric soil. Well, now it's a wetland, and now you're following wetland policy, and now so it is relative to, yeah, we want to get it close, but like I said, there is a very high importance on getting the color to that, because you're talking, I'm not getting political or policy and all that, but that is why that is there.
Soil texture, as I mentioned on the PowerPoint, it's qualitative, right? And qualitative means we're just doing it like, a guesstimate in the field, while we back it up with quantitative numbers, which is lab analysis. In the field, we do this qualitative method, and we follow something very similar to this flow chart. And when texturing soils, what you want to do is you want to get about a golf ball or egg size amount in your hand of dry soil. For example, we're going to do this loam, so you can get yours. Good. Yeah, about a good little handful. And you can get some. And the cool thing about these soils is we already have texture analysis, so you can see, okay, this is 16% clay, and this is this amount silt. So you get some here. And when you texture, what you want to do is make sure to break down all these little aggregates. And if you these won't have any, but if you have any plant roots or any rocks like that, any organic material, you want to take them out of your sample, because that could mess with the results a bit. Oh.
How wet do you like it? Is it too wet for you?
No, so you'll know if it's too wet if you like squeeze in your hand and water's coming out. That's probably a little too wet. But if you break it open and see some like dry spots, then it's a little too dry. So you're probably about getting there. So this one is a straight loam, and notice how it's like kind of a little hard to get into a ball, or it feels like it's kind of breaking up a little bit. You're not getting that? Okay, maybe
Too
so.
wet?
No, maybe mine's just not broken down enough.
I mean, if I.
It's like I got poop in my
Oh yeah. Did you get?
I did the silk.
Oh, you did the silt. Okay, so the silt is going to have, and we have the soil texture triangle here. So the silt is also going to be breaking down a lot too. Yeah. But if we're going to follow the diagram with you guys, so we've got our soil amount, and then one thing you can do is throw it up into the air. If you catch it and the ball doesn't fall apart, that means there's probably not going to be a whole lot of sand. You're going to have a little more clay. And if we go down this diagram to really kind of estimate what the texture classes you have, you want to start forming a ribbon. So what you can do is get in your hand and then just start moving it up. And if your ribbon breaks apart a little too fast, you can get it wet again. And you want to do it a couple times, because you might get a false positive or false negative, if you will, on texture class. So let me get a little more water here. Squeeze out the excess, and then try to get a ribbon going. Yeah, so this one I ain't ribbon too well right now. But on that ribbon, what you get?
About 2 centimeters.
About 2 centimeters, so about less than an inch. So did it form a ribbon? Yes. It was less than that. So next part, what you can do is you can get a little piece of like a little BB size amount and put it in the middle of your hand. Soak it with water and go ahead and give it a feel. Like, do you feel a lot of sand particles? Do you feel it real gritty? Do you feel it real smooth? Is it sticky?
Very smooth.
Very smooth. Okay.
There's very little stick to it, but I can see it's also sticking to my hands.
Very smooth.
It's
so
very smooth. Feels like flour.
So it's either going to be a silt loam or a loam, and this soil that you got was a loam, so that kind of puts you in the right direction. Now, there is some nuance to it. I mean, it's just going to be, I guess, based on your experience with it, right? But that's where you would, in our case, back it up with a lab analysis.